In today's lab, I'm going to explain you about interrupts and how to do small experiments on interrupts in the 8086 emulator. Right? Since interrupts have not been covered in the theory class, first I'll give you a small insight into what is interrupts. Okay, there are some hardware interrupts and software interrupts in 8086, but essentially we will focus on software interrupts, what it is. Okay, software interrupts is whenever we are writing a program, we can we can call for an interrupt subroutine by writing a command int followed by number. Okay, so that number is from 0 to 256. So there are 256 kinds of interrupts which you can write. So an interrupt followed by an 8-bit number, right? An 8-bit number. So 1 to 256 you can write there, right? 1 to 256 is in normal decimal number. So there are because it's an 8-bit number. So otherwise you can write it in hexadecimal number, whatever is the interrupts. Okay, so when you call for an interrupt, what happens is, okay, the current whatever is the IP address, okay, and before the IP address the flag also, okay, the flag is put into the stack register, okay, and then the contents of the within the flag you have IF and the TF flags. Okay, this is the interrupt flag and the trap flag. They are cleared, they are set to 0 because now since already one interrupt program is being serviced, so that's the reason these flags are set to 0, and then the current CS and IP is pushed into the stack register, and this program jumps into the interrupt subroutine. Now where to jump? So there are, I told there are 256, they can be 256 different interrupts. Okay, so what it depends on what interrupt you have called for, interrupt 1 or interrupt 256 or interrupt 21, whatever you have called for. So what it will do is, once you have called for, say for example, if you have called for interrupt 21, okay, so there will be something known as the initial memories of the code. If you see from 0000 to 256, okay, if you see, this is corresponding to 256, right? So these memory locations are earmarked for these memory locations are earmarked for storing the interrupt vectors. Interrupt vectors, when I mean, when I call for example interrupt 21, so it will go to in the memory location, it will go to corresponding interrupt 21, and it will have 4 bytes of information, and those 4 bytes will be the IP address and the CS where you have stored an interrupt program corresponding to 21, right? So the program will jump to that place. Okay, is it understood or is there any confusion? Okay, let me repeat it once more. When I call for interrupt 21, okay, so the program has to jump somewhere and start executing it. Okay, where to jump? Okay, where to jump, that information is given in this vector table. So for each type of vector, type interrupt, type 0 interrupt, type 1, type 2, type 21 vector, in type 21 vector, okay, what is the information which requires, what is the IP address and what is the CS, that will be picked up from this vector table. So once you pick up that address, then the program will go to that address, okay, whatever is indicated in the vector table corresponding to the interrupt which you have given, and in that memory address there, starting from that memory address, you can write an interrupt program. Okay, once that program is written, at the end of the program you write an return, like an interrupt program is written here, and end of that interrupt program a return is written, and it will the program will come back to the main program. Is this loop of interrupts understood by all of you? Anybody has got a doubt? If it's not clear, let me know. Okay, I can explain it once more. Is it clear to all of you? Yeah. Okay, then we will move forward. right? When we in today's experiment, we are going to learn about interrupt 21. Okay. So there are I told there are 256 interrupts. So around first 5 are generally fixed, and then next 30 are also pre-programmed, okay, by the Intel only. So after that we can create interrupts, okay, when we write. But interrupt 21 is one such interrupt which is programmed by Intel itself. Okay, it will be available in the it will be already available in the hardware what you buy, or even in the EMU emulator. This interrupt 21 is already programmed, so you don't have to write the program, okay, for this interrupt 21. Okay, so interrupt 21 also, when we initiate interrupt 21, okay, what will the microprocessor do? It will push the information of the IP and the CS and the flag status on all these three information into the stack, and then it will refer to the vector table about the interrupt 21, and it will go to that memory location where this interrupt and program has been stored, and it will start executing. So within the interrupt 21 program, one of the first commands will be to read the contents of AH. Okay, so that is why we need to give the before we start the interrupt, we need to initialize AH with some contents. Okay, so because the interrupt program where 21H, okay, when it is initiated, it will the one of the first instructions within interrupt 21 program would be to read the contents of AH, and accordingly then it will make a jump and execute one of these functions. So within interrupt 21 there are several functions it can do, like if I load move AH as 1, okay, and then the interrupt 21 A1 means it will read a character from a standard input, and it will echo the input which is being read onto the standard output. Okay, so this AH is equal to 1 means that the program is going to read an input from the standard input, which is the keyboard, and then and give the same input what it's reading. It will be available in AL register, and it will also be displayed in an it will be sent to the display. Okay, so this is the program it would interrupt for AH is equal to 1. This is the one, and the first one would be applicable. Now similarly, if I give AH is equal to 2 and then write interrupt 21, when the program is executed, then the interrupt will, what it will do is it will write a character to the printer. So whatever is available in BL register, okay, that will be written on to the printer. Okay, if there is a printer connected, so that will be printed. Okay, so that is what happens when if you have AL is equal to okay, this is AL is equal to 5, it's written out here. Okay, AL is equal to 2, I think it will display into the instead of printer, it will the character will be available onto the display. Similarly, you have a 2A. Okay, if you write move AH2A and then you write interrupt, the whatever is the system time available, so that will be available into some registers. I will explain you that subsequently. So there are various, depending on AH, the interrupt will jump into one of these sub program in one of these functions, and it will accordingly do that. Okay, so I'll do a small demonstration so things will be clear to you, right? This is like the first program which you have to do, which is move AH1H, and then you do an interrupt command. So you will find that it will ask for you to give some input from your keyboard. So once you do that, that will be displayed here. So since 88 emulator no display is connected directly to 8086 emulator, so it has got an simulated display box out here, but your keyboard will be the same keyboard which you are using on your laptop or your PC. That will be taken as an input port, and the output display will be a simulated window will be shown here. So whatever you type here will be displayed here. Okay, so for one interrupt AH is equal to 1, okay, whatever you type will be captured in AL, and also will be, it is an echo. Okay, so there is one more interrupt which only reads, there will be no echo. One H stands for echo also. Okay, so that means it will whatever data is captured, it will be in AL register, as well as it will be displayed in this window. Okay, so we will see the demonstration, then things will be clear, right? Then this is another interrupt 2H, in which whatever you write in DL, that will be captured into AL register. No, that will be shown into the display. Okay, so whatever is available in DL, that will be available in the output display. So this is the second interrupt which you need to do. Okay. This is a read system date. Okay, so you move 2A into the interrupt, and then when you run the interrupt, okay, then you will find that date is available. So the CX will indicate the year, DH will indicate the month, and AL DL will be the date, and AL day of the week. So this will be captured in these registers. So you can use this interrupt, and these are some of the review questions which you can go through. I will upload the PDF. Then 2H is to write the standard output. Okay, this I think I already explained you this. It will give the standard output onto the screen, whatever is available in DL. Okay, this you need to do it yourself, printing of an string. Okay, so this is available in one of the in the memory location message. Okay, and you start the code, then you write move x at the rate data. Okay, when you write at the rate data, what happens is the memory, this is like it's almost equivalent to load effective address. Okay, so you can write move ax at the rate data, so the effective address and LEA, so the memory of the data will be stored into AX. Okay, and then move DS. So the the data address is being loaded into the DS segment out here. These two commands. Okay, so after that you move the offset of the message. Okay, the first one is just putting whatever, wherever you started the data, you are initializing DS with that, and then you are taking the offset of the message. Okay, that means this message, address of the message, into DX, and then you are moving AH9 and interrupt. So interrupt 21 along with AH is equal to 9 will actually start a string operation starting from the address given in DX. So that is why we are moving the offset message into DX. Okay, so to understand these what are 21.9H stands, you can Google or you can refer your textbooks. So what 21H and AH09 indicates. Okay, so what it indicates is it is a string printing string operation. This interrupt is a printing of string operation in which the offset address has to be stored in DX. Okay, so it will, from DX onwards, it will start the string operation. Okay, printing of the string operation. But how do you come to know where the string is coming to an end? So whenever we write a string, it has to be ended with a dollar sign, so that the microprocessor comes to know, okay, this is the end of the string. So that is why you will see that there is an dollar which is written here. Okay, so this you need to do it yourself. Okay, so this is there. So let me just give a small demonstration because it's slightly new to all of you. I'm writing move age 01 h and then int 21, right, and then I am emulating it. Okay, move. Okay, so this has come here. So if I run, okay, not supported it. Okay, I have not written hexadecimal out here. So you see there is a display which has come out here, right? So if I press 1, so this has come. Okay, so the 1 has got printed onto the display. If you see the display here, 1 is available here, and also if you see the register out here in the AL register, 1 has been captured. So I pressed 1. So if I reload it, okay, and then run again, it will ask for the keyboard input. Okay, now I am writing an A. So if you see A has been captured out here. Now A is available in the display, and if I see in the AL register, okay, also okay, so on the display A is available. Okay, now what I can do is if I want to make a loop, okay, I can also do a loop out here. So let me write something on jump again, and I have written out here again out here. Then I am doing an emulation, right? So I'm going to run it. It's going asking me keyboard input. So I am writing A, right? Now what, it is not come out, right, because I have put a jump again, and so it's become a loop out here. Now I can write an A, B, C, D. So whatever I am typing is coming here, 1, 2, 3, 4. So whatever I am typing, that is being read, and it is being displayed out here, right? So if you see the corresponding hexadecimal last whatever is there, ASIC code, like if I am writing alphabets, the ASIC code is available right here. So if I am typing 2, 4, right, so accordingly this is being it's coming out here. So this is how this you got to try it out, these contents. Okay, so this is one, and then let me show you one more. Right, if I write move AL into 2, right, and then I write move in BL, say within inverted commas, it is going to take it as a character. I run this. Okay, I run. Okay, because I have given a jump command out here, it's gone into a loop. Let me remove that. Read it. So if you see in this window, okay, in BL I have given A out here, right? So if I run, so A will be displayed in this window out here. Okay, so another thing what we can do is, one more example like I'll show you is in AH, now we are going to write an 2 A, right, and then we are going to use the interrupt. '21. So if I do this, so if I run it, you will find in AL register it's showing 0 5. 5 means today is Friday, right? So that is why it's showing. In CX, if you see in CX, it is 07 E5. Okay, that is 2021, right? It is showing that value there. And then in BH, right, where is in yeah, and CX it's year, and DL, in DL it is the date which is there. Okay, this is in DL it's showing 13 19 13 it's showing in hexadecimal, which is 19 today's, and this is the month 03. So you see the date has been captured. Okay, so now I think I given some demonstration on various interrupts, so you can do that.